Hello and welcome to this next lecture on fundamentals of acoustics. We've been looking at some applied topics. So along those lines, let me just mention the kinds of impedances we have seen, okay, so far. One is of course mechanical impedance. Which is force over velocity. Then we have seen specific acoustic impedance, which is pressure over particle velocity. Okay. In many lectures I have referred to it as acoustic impedance, but I have mentioned that it is actually specific acoustic impedance. Okay. Now the third is the actual what is called the acoustic impedance, which is pressure over volume velocity, okay, which we used in branched systems. Okay. In branched systems we use this quantity. Now there is another, all of them carry similar or same implications. Okay. The word impedance is crucial here. How difficult does the driver find it to drive the medium? Okay. Now one more impedance we will see is the radiation impedance. Okay. It has mechanical impedance unit. So let me give the symbol that tilde ml. Let's call this, I have given it Z tilde A. Okay. So this is acoustic impedance, sorry. Can give this Z tilde Q. This has mechanical impedance units, okay, and it will call it Z tilde R. What this is essentially on the surface of the radiator, we do this integral of the surface pressure divided by surface velocity ds. Okay. So what does it tell us? It tells us how the radiator surface sees the medium that it's driving, mostly air. Okay. See the medium that it is driving. Okay. So now let's look at this pulsating sphere. Okay. The pressure at a radius r at a time t was given by j omega rho 0 1 plus jka q by 4 pi r e to the power of j omega t minus k r minus a. Okay, and the surface velocity, it's a pulsating sphere, so it is u0 e to the power j omega t. Now if you are going to implement this, okay, I have this integral over the surface. The pressure is j omega rho 0 by 1 plus jka q by 4 pi a e to the power of j omega t. Why? Because r is a. This r becomes a. Okay, here r becomes a. Okay, please note that. Then divided by u0 e to the power j omega t, and a square into differential solid angle. Okay, and everything is constant. The solid angle is 4 pi. So if the integral is done, I get a 4 pi. Okay, so let me not do that. I have this integral a square d omega. Okay, so this is zr. Now the zr looks like what? It looks like now j omega rho 0, q is 4 pi a square u0 divided by 4 pi a u0 into 4 pi a square. Okay, so if I do this, 4 pi goes, this u0 goes, I get an extra a over here, and I forgot the 1 plus jka. Okay, so that is the radiation impedance. Okay, so now what is it? If I write it, radiation impedance is j omega rho 0, okay, by 1 plus jka into 4 pi a cube. Okay, so now we will specialize it. We will specialize this expression for Ka very small. That means we take it to the monopole approximation. Monopole approximation. Okay, if we do that, z tilde r Ka much smaller than 1 is j omega rho 0, okay, into 4 pi a cube. We will write this as j omega rho 0 into 4/3 pi a cube into 3. 4/3 pi a cube is volume of the small sphere, volume of pulsating sphere. Okay, into rho 0 is mass of air, with volume of sphere. Okay, so this is m, and so I get j omega thrice m. Yeah, it's very informative. Why? Because all impedances carry the same connotation, I said. So this first of all imaginary. So essentially not much power or no power, not an efficient radiator. Efficient radiator. And to this little sphere, how does the rest of the medium look like? It looks like a mass, okay, or what is it, 3 times the mass. Okay, mass of what? Mass of air with the volume of the sphere. So this, okay. And therefore it is not a dissipative element, it is an inertial element, and inertial element will exchange power, exchange instantaneous power, okay, and therefore time average power will be 0, okay, all these implications. That means it is not an efficient radiator. On the other hand, if we look at this Z tilde R is equal to j omega well Z tilde R for Ka much greater than 1, okay, then from here we get Z tilde R is equal to j omega rho 0 by jka into 4 pi a cube. J goes, k is omega by c, so I get a c on top, omega and k go, this a goes and I get an a square, so I get rho 0 c into 4 pi a square, or rather rho 0 c into s, which is like a mechanical impedance, and it is real and therefore absorbs power. It is dissipative. The source sees the medium as something that takes power. So the source is efficient. So either when the frequency goes up, k goes up, k is equal to omega by c, so omega goes up, or the radiator size goes up, so that Ka goes up, okay, radiator size goes up, more volume is pushed, okay, frequency goes up, then when frequency goes up, air has no means of escape. Air has no means of escape. What do I mean by that? If I have a piston, okay, that is oscillating back and forth, and there is no baffle around it, when this piston tries to push the air in front, and somebody is standing here, this is the ear, the forward movement pushing the air, compressing the air, because there is a root, the air will escape to the back side of the piston because there is no wall, okay. Similarly, when the piston tries to push the other way, this air moves forward. So there is a local sloshing, there is local activity. As a result, very little sound reaches the ear of the observer, okay. Instead of that, if we put a baffle, that is the reason we put a baffle around it, then this air has no way to escape to the back side, and therefore when the piston compresses, compressions have to move forward. Compressions and derivations have to move forward, so it becomes efficient. So that is why a speaker has a cabinet around it. Speaker is circular with a cone, but you build a cabinet around it. Why? because you don't want this back communication of air. Okay. Now along the same lines, say that there is no baffle at this point. Okay, baffle is not there at this point, and now the piston is oscillating back and forth. Okay, so that there is back communication happening. But if the piston starts to oscillate at a high frequency, piston is oscillating at a very high frequency, then also air, because it has inertia, will have a difficult time escaping. So even a piston without a baffle will become efficient if frequency goes up, and even a piston without a baffle becomes efficient when its radius goes up. Okay, so Ka is that number. Okay, so that's as far as the sphere is concerned. Okay, now let's just look at this aspect here, the power aspect. Okay, power is essentially intensity into area, which is 1/2 the real part of PV conjugate into the area. Okay, or now in this case it is 1/2 the real part of the radiation impedance into the magnitude of velocity squared. Okay, so this is mechanical units, so we don't need any more area. Okay, so now we have the sphere. Sphere has what? Sphere has z tilde r given by j omega rho 0 by 1 plus j k a into 4 pi a cube. Okay, so now we work on this, and what we do is we take j omega rho 0 into 1 minus j k a by 1 plus k square a square into 4 pi a cube. Okay, so this happens to be j omega rho 0 4 pi a cube may not go that route, we just do it here. Okay, so from here, if z tilde r, which k a much less than 1 is given by j omega rho 0 4 pi okay, let me do it, sorry, let me do it. So we have j omega rho 0 plus into 1 minus j k a by 1 plus k square a square into 4 pi a cube. Okay, that gives me j omega rho 0 4 pi a cube by 1 plus k square a square plus omega rho 0 k a by 1 plus k square a square into 4 pi a cube. Okay, this is the real part. Okay, this is the imaginary part. Okay, the real part is called the resistance, the imaginary part is called the reactance. Okay, so now that is the situation. Okay, now let's see, if Ka goes to a small value, okay, if Ka becomes small, when Ka becomes very small, what happens? We have j omega rho 0 4 pi a cube, okay. So as xr part plus Ka is small, so omega rho 0 Ka 4 pi a cube is the real part, okay. So if we rewrite this z r tilde for Ka small, okay, I divide by a c over here, multiply by a c, okay, that gives me K rho 0 c j K a rho 0 c 4 pi a squared plus, okay, I do the same here, divide by c, multiply by c, okay, so I get rho 0 c and k square a square and 4 pi a square. So if I take 4 pi a square outside, which is the surface area, I get j times Ka rho 0 c plus rho 0 c k square a square, okay. So this is r of r, this is x of r. Now we want this power 1/2 the real part, okay, z r tilde v square, okay, then get 1/2 rho 0 c k square a square into u0 square into 4 pi a square, okay. Okay, along the same lines, when z tilde r Ka is much bigger than 1, okay. So from here what do we get? We get equal to j omega rho 0 4 pi a cube by k square a square plus omega. So the idea is that it's proportional to Ka or K square or K square, that's the idea. And so as Ka becomes smaller and smaller, the power becomes reduced, okay. I suppose you got that idea. For small Ka, it is proportional to Ka or Ka squared. So when Ka goes small, K square goes much smaller, and then the power reduces, so it becomes an inefficient radiator for this condition. On the other hand, when we have this condition, I have this plus omega rho 0 Ka by K square a square 4 pi a cube, and this becomes you can keep it like that, multiply by c, divide by C. So this becomes J K rho 0 C, J K rho 0 C, and I will bring in one A here, rho 0 C, take out one A here, divide by K square A square. So that this goes and I get a Ka in the denominator, Ka. Okay. So as Ka becomes bigger, this imaginary part starts to reduce. Okay. Now what about the other side? The other side is I have plus divide by C multiply by C, so I get K rho 0 C, then I have Ka over here, and I have 4 pi A cube over here. So I take an A square, bring an A square, bring this here, divide by K square A square. So this goes away, and this approaches rho 0 C into an area which is surface area of the sphere. Okay, this is the plane wave impedance, plane wave mechanical impedance. Okay, and what is the meaning of that? The pressure and particle velocity are in phase, and so radiation happens efficiently. And there is a small imaginary part which is reducing. Okay, so we have not made approximations here. As we say, K is large, we remove 1, K is small, we keep only 1, but without approximating, this is what happens. Okay. Now let us look at another case here, which is our piston in a baffle. Piston in a baffle. Okay. Piston in a baffle, if we do the same calculation of radiation impedance on the surface of the piston divided by particle velocity and ds, okay, that ends up looking like R of R plus Jx of R. The details are there in Kinsler and Frey, which is a textbook for this course, Fundamentals of Acoustics, Kinsler, Frey. Okay. Now this is a very tedious calculation, so we don't go to the details here, but R of R is now pi A square rho 0 C into some function R1 twice Ka. Okay, and how does R1 of twice Ka look like? It looks like, or let us see before that, R1 of x looks like, it looks like 1 minus twice Bessel function cylindrical first kind over x, okay, which is, if you do an expansion, is x square by 2 square into 2 factorial, okay, minus x to the power 4 by 2 to the power 4 into 2 factorial, 3 factorial, and so forth. Okay. And what is x1 of x? X1 of x looks like 4 by pi x by 3 minus x cube by 3 square into 5 plus etc etc etc. It's a series. Okay. So now Ka much less than 1. What do we have? We have R1 of x given by x square by 8, okay, and here we need x equal to 2 ka, so 2 ka whole squared by 8 is equal to k squared a squared by 2. That means what? My r of r is equal to pi a square rho 0 c k square a square by 2. What about xr? xr also takes the first term, which is 4 by pi 3, x is 2 ka, okay. So that is xr part of it. So I didn't mention, let me mention that. xr is equal to pi a square rho 0 c x1 of 2 ka, okay. So xr is x1 of x into pi a square rho 0 c, okay. Let me write it. R of r is pi a square, the piston area, rho 0 c 1/2 ka whole squared, and the x of r is again pi a squared rho 0 c 4/3 pi into 2, so 8/3 pi into ka, okay. Okay, so let's see. So this of course is proportional to ka, so r of r will be small, okay. If r of r is small, then this power function will be small, okay, and so it's an inefficient radiator already, inefficient radiator, okay. But what about the reactance part? Okay, this now looks like pi a square into I'll take k as omega by c, so I get an omega over here, okay. So the and I get a rho 0, okay, and I get 8a over 3 pi, okay. So this is the piston area, this has length units, okay. So I have omega into the density into a volume. What is that volume? Volume is base area pi a square and a length 8a by 3 pi. So base area is the piston area pi a square, and there is a length to it which is 8a by 3 pi. Okay, so that means what? The rest of the medium looks like a cylinder, okay, with a base area pi a square and a length of 8a by 3 pi. Okay. So, for small Ka, if this is ignored, Rr is all nearly 0, then the reactance dominates, and the reactance, how does it look like? It looks like a mass first of all. So, inertial, the rest of the medium is inertial with a base area this much and a length of this much, and therefore, the mass exchanges. It is not a dissipative element, it exchanges instantaneous power, so that largely the time average power is 0, and the piston is inefficient. Okay. For Ka much greater than 1, the R1 of 2 Ka is equal to 1. This value is 1, so that R of R is pi a square rho 0 C, and x1 of 2 Ka is 0, so that xr is 0, and R of R is pi a square rho 0 C. Okay. Now, that is rho 0 C into S, which is the mechanical impedance of a plane wave. Okay. And therefore, it approaches a plane wave. Which means the pressure and the particle velocity are proportional, and so you have an efficient radiator. Okay. So, that is one last point I want to make is this, that if we have a pipe, open ended pipe, okay, the pressure condition is actually 0, that is the boundary condition. But if you actually put your ear over here, you will hear a sound. Okay. Now, the impedance from the piston is J rho 0 C tan KL. Okay. So, now what happens is that there is an effective length. If this is the length that is there is an effective length which is L plus A delta L is equal to L dash. So, the impedance ends up as rho 0 C tan KL dash. Okay. Now, this delta L is 8A by 3 pi if the pipe is flanged. Okay. What do you mean by pipe is flanged? I have a pipe, the end of the pipe, and the pipe is placed in a wall. Okay. Pipe is placed in a wall. This is flange, this is a flange. Okay, that is the correction you need this correction to get correct values of resonances. Whereas if it is not flanged, unflanged, okay, the pipe just ends at unflanged. The correction is approximately 0.6 of A. Okay. That means in this case you have to look for tan of KL plus 8A by 3 pi K equal to n pi for resonances. Okay. K into L plus delta L. Similarly here also. Okay. I will close the lecture here.